Oh, mais ouais, j'ai tout présente, mon frère Antoine. Merci. Hey, comment allez-vous? It's good? It's good? Ah, trop bien. Antoine, un place, por favor. That was Spanish.
Okay, can you hear me? Is it good? Comment allez-vous? Okay, so I'm gonna be talking about building a background job processor from scratch. So myself and two other software engineers, we decided to build one to shed some light on background job processors because most of applications use them and we don't, some people don't really know how they work, or at least there's a lot going on in the background. So we built one, actually, it's called Workaholic. You can see it's a robot juggling beers. So you can see here we have a little demo. Workaholic has a CLI, so you can configure the background job processor to execute in different ways depending on your use case. It supports concurrency, parallel processing. It integrates with Rails. The app you can see here is a Rails application. I don't think I can zoom in. It's a GIF, so I'm sorry. I'm sorry. It's okay. It's not meant. You don't have to read it. I'll explain. It's just an overview. It's okay. Don't worry. It's okay. So, as you can see, it also has a web UI that reports real-time data and some historical data. I'm going to dive into how we built it, and if you want to build one, how you could go about it. It's in alpha stage, so do not use this in your production applications. It's not meant to be used. It's more to shed some light. We have a detailed write-up. I have a link at the end of the talk, so you can look at it. Okay, so let's get into it. So I'm going to talk about the core features of a background job processor first that we thought belonged in a background job processor, and then I'm going to talk about the nice-to-have features. So first, we want to have asynchrony. I'm going to present a simple use case, a simple example, why we would want to have asynchrony. So let's say you have a web application running on a web server. The client makes a request to this web server, and then it needs to send an email. So you could do this synchronously, but you're going to have to send a delayed response back to the client. So that's where a background job processor comes in. You can process the job asynchronously by delegating it to the background job processor and return an immediate response to the client. This way you don't hold the client spinning and you can just send the email asynchronously. So how would we go about doing this? So what we did for Workaholic is that at first we had the code embedded in the application code. So it would be done synchronously. You would have a job delegated to the background job processor synchronously. So to make it asynchronous, we decided to have Workaholic execute in a different process, another process. But the problem that arises when you do that is that how do you communicate these jobs to the background job processor? And so what we did is that we used a data store as an intermediary between the web application and the background job processor. We decided to use Redis. So the application serializes the job and then stores them in job queues. And then we have Workaholic that has workers polling the jobs, processing them. The job processes successfully. It stores some statistics inside of Redis. And then if it fails, it's going to retry the job thanks to the job scheduler, which will schedule the job at a later time. And then once the job is due, it's going to enqueue it back in the proper queue. Okay, so now let's talk about reliability. So we want a background job processor that's reliable. Why? So what if your application crashes? What happens to your job? What if your background job processor crashes? What happens to your jobs as well? What we did for Workaholic is that we use Redis. So we rely on Redis and its robustness in order to store the jobs and persist the jobs. So if your application crashes, the jobs that were enqueued are stored in Redis and are saved there, they're persisted there. If your background job processor crashes, the jobs are stored in Redis as well. But there's another thing that we need to consider when we talk about reliability. It's what if the job itself crashes? What if you have a network error? What if you have an exception that's raised inside of your job? That's where the retrying failed jobs component comes in. So you want to retry your jobs if they fail up to a number of times. In Workaholic, we retry the jobs up to 5 times. And the way we do that is that we use a sorted set in Redis. So we use the job scheduler. The job scheduler stores the job to be retried in the scheduled set, in the sorted set. So a sorted set in Redis, it's composed of members. Each member has a score and a value. The score is used to sort the set. So what we did is that we used the job execution time, so the timestamp at which we want to execute the job, as the score for the job, the member in the sorted set. This way, you can then check with the job scheduler if the job is due by checking against the current timestamp and the timestamp that's used for the score in the sorted set. And if it is due, you want to enqueue that job back in its proper queue so it can be retried and executed again, processed again. Now, the other thing that you have to consider is what if your background job processor is executing job, but you want to stop it? How do you make sure that you don't lose the job that are currently executing? So what we did for Workaholic is that we rescued the system exit error and the interrupt error, and we gracefully shut down. What does it mean? Gracefully shutting down means waiting on the workers to be done executing. And the way we do that is that we kill the workers in a graceful way. We wait for them to be done executing. We also kill the other components in a graceful way, waiting for them to be done executing. And then we exit the program, as you can see right here. Okay. So now let's talk about efficiency. What if you want your background job to be efficient? And why would you want your background job to be efficient? So let's take an example scenario. Let's say you have Rails application, has 1,000 QPS, so it's a pretty big Rails application. Let's say 10% of these requests are gonna involve sending an email. Let's say 1% of these requests are gonna involve processing images. And let's say that this Rails application takes 400 megs in memory. It runs on a server that has 4 gigs of RAM and 4 CPU cores. Okay, so that's a scenario. Now let's look at what it means to be efficient and why we would want to be efficient in this case. Okay, so we are sending emails, and let's say an email takes on average 50 milliseconds to send. If we take a 24-hour window, we're going to have to send 86.4 million requests. We're going to receive 86.4 million requests, sorry. And 10% of these requests involve sending an email. That means that we have 8.64 million emails to send as that are going to be executed as background jobs. In 24 hours, we can only send 1.73 million emails. So that means that we're going to have a buildup and a backlog of jobs that's going to build up every day. So after one day, you're going to have 6.91 million jobs that are still enqueued in Redis and that you still need to execute and you still need to send this email. So what does it mean? It causes 2 problems. The first problem is that you're going to have a latency that's dramatically increased. And what does that mean? That means that the next day, the first job that you enqueue, you're going to have to wait 96 hours before it's executed. So that's not possible. It's not sustainable. And in terms of memory, every day, you're going to have 171 megabytes of jobs that are a backlog of jobs that are stored in Redis. So for Workaholic, we computed the average of a serious job, that the space that it takes in Redis. It's around 26 megabytes. So what we can see is that in 24 days, you're going to hit the storage limit. If you have a 4 gig machine, in 24 days, you're going to hit the storage limit. So what are the solutions? The thing is that we want to have a better processing throughput. We want to process more jobs at once. So here we have a 1:5 enqueuing to processing ratio, which means that in 24 hours, we enqueue a certain amount of jobs, and it's going to take 5 times longer to execute them, which means we need to process 5 times faster. So how did we do this? What we did is that we use concurrency. So in Ruby, concurrency is enabled by using threads. So in Ruby, since 1.9, threads are actually OS threads, which means that they rely on the OS scheduler to be scheduled. And the OS scheduler is going to schedule your thread on CPU cores. So we have 4 CPU cores. We could have 4 threads scheduled in parallel. But if you're using MRI, you have the GIL. The GIL is the global interpreter lock. And what it does is that it prevents from having multiple threads scheduled at the same time on different CPU ports, which means that you can only have one thread scheduled at a given time on the CPU port. So how does that help us? Well, the thing is that sending an email is an IO bound operation, and MRI is smart enough that if you have an IO bound operation executing inside of a thread, it's actually going to put this thread into a sleeping state, which means that the OS scheduler is going to be able to schedule a different thread. And effectively, since it takes 50 milliseconds to send an email, it's probably 99.99% of the time of execution, which means that you can have 5 threads sleeping in parallel. And this way you can increase your processing throughput by 5. You can multiply it by a factor of 5. So we're not crazy. We have some benchmarking to prove this. Here we have 10,000 jobs. So non-blocking jobs, IO blocking jobs, CPU blocking jobs. For the IO blocking jobs, as you can see, there's a difference when you use multiple threads. If you use one thread, it's going to take 5,000 seconds to execute. And inside of an IO blocking job is actually a sleep of 500 milliseconds, which we estimated on an API, GitHub API call. So with one thread, it takes 5,000 seconds to execute 10,000 jobs. With 25 workers, 25 threads, actually it takes 25 times less. With 100 workers, it takes about 100 times less, which means that it's about a factor of the number of workers that you're going to increase your processing throughput. Okay, so now in Workaholic, a thread is mapped to worker, or worker maps to a thread. So let's show some code. Here, as you can see, you have the worker. When it starts working, it spins up a thread. In this thread, you're going to want to pull the jobs from Redis, and then you're going to want to process that job. That's simple enough. Now, the thing is that we want to consider the impact on our hardware resources. So what's the memory consumption of a thread? So when you have a Ruby process, you have a main thread in which your main code is executed. And then when you can spin up new threads, you can spawn new threads, child threads from that main thread. So the main thread is going to have a stack and a heap in terms of memory. And each thread, each child thread is going to have its own stack. But the thing is that with threads, they're going to share the same heap as the main thread, which means that the impact in terms of memory is going to be relatively low, and threads are going to be cheap to spawn. Here we have, we benchmarked the REST application, which would take 112 megabytes when we have one thread, and which would take 125 megabytes when we have 25 threads. So as we can see, the memory consumption is pretty low. Now, the problem is that when you introduce concurrency, you also are introducing potential rest conditions. What are rest conditions? So rest conditions is the fact that you can have multiple threads scheduled by the OS that are compete to try and modify a shared resource. That's on the heap, as we saw right here. You see the heap is shared, which means that any resource on that heap can be modified by the threads, which means that multiple threads can be just stopped by a DOS scheduler and then can try to modify that resource at the same time, and that introduces rest conditions. Now in Workaholic, we made sure the code is thread safe, but the user space code might not be, which means that our jobs and the jobs that the user is gonna enqueue needs to be thread safe. Now, I have an example, but it takes like 5 minutes or so to explain. So if we have time, I can show you at the end of the talk. So we solved the problem and the processing throughput. We increased the processing throughput. So we have now a one-to-one enqueuing to processing ratio for the emails. What about the image processing jobs? How is it different? Can we use the same thing, the same concept, concurrency and threads to solve this problem? Well, let's say an image processing job takes 4 seconds on average to execute. We have a 24-hour window. We're going to have the same amount of requests. 1% of these requests are going to involve processing an image or processing images, which means we're going to have 864,000 images to process, for example. Now, in 24 hours, we can only process 21,000 images. So what does that mean? That means we have a 1:40 enqueuing to processing ratio. Okay, that's pretty bad. But what does it mean in terms of latency and in terms of memory consumption? So we have a backlog of jobs of 842,400 per day because we're only able to execute 21,000 jobs, which means that we're going to have a latency increased by 936 hours per day. The same thing as before. If you enqueue a job the next day, you're you're going to have to wait 936 hours before your next job is executed. Okay. Now, in terms of memory, we have the same amount of memory taken for a serialized job. So here, the impact on memory is lower, but it's still not sustainable. You have 196 days, you're going to run out of memory. Okay. How can we solve this problem? How can we even balance out the enqueuing and processing throughput? And here we have to increase the processing throughput by 40. We have to multiply it by 40. Okay. So what we do is we introduce parallelism. Why? Because as I said before, if you have a CPU-bound operation, it's not useful to have multiple threads because you have the GIL in MRI. Now, what you can do instead, and since image processing jobs are CPU-bound jobs, is use multiple processes. And in Ruby and MRI, you have the process API that allows you to fork a process from the main process. So from the parent process, you can fork child processes. So here we have 4 CPU cores, which means we can fork 3 processes and have 4 processes running in parallel, scheduled by the OS scheduler. Now that brings down our ratio from 1 to 40 to 1 to 10. Before we go further and we try to improve, again, this ratio, let's look at the impact from forking processes. So first of all, in terms of benchmarking, in terms of time that it takes to process CPU-bound jobs, having 2 processes takes about half the time to process the jobs as if you had 1 process, which means that if we have 2 processes, then we multiply the processing throughput by 2 for CPU-bound jobs as well as for IO-bound jobs. Now, in Workaholic, it's going to look like this with our current example scenario. We have 4 CPU cores. The OS scheduler is going to schedule 4 processes, which each have 5 threads. And then each thread is going to map to worker, and the worker is going to pull from Redis to process the job. Okay. Now, in terms of memory consumption, it's going to take much more memory because when you fork a process, a child process has a heap and a stack that are independent from the parent process. Now, there's a copy on write mechanism that's in certain operating systems that can be used in order to limit this impact, but we cannot assume that it's always going to be the case or that we are always going to have lower memory consumption because we have this mechanism. And this mechanism, the point is that the child process can reference the parent heap until it actually modifies the data on that heap. If it modifies the data, it copies it over and modifies it on its own heap. We ran some benchmarking to check how much memory it would take. So we have the same Rails application as before. It takes 125 megabytes. And then if you have 2 processes with 25 threads each, it takes 200 megabytes of memory. Now, there's the copy and write mechanism at play right here, but we cannot assume that's going to be the case every time or that not all the data is going to be mutated, which means that in our example, as I said, we have 400 megabytes for our Rails application, which means we're going to take about 1.6 gigabytes of memory if we spawn 4 processes. So that means that we're fine in terms of memory consumption. Okay. Now let's look at scalability in order to increase the processing throughput so we can even it out with the enqueuing throughput. As we saw, we have a 1 to 10 ratio right now. So we need to do better. And how can we do better? We can do better by scaling. So what we can do is that we can scale vertically. So if you have, we have looked at DigitalOcean and their best machine has 20 CPU cores, which means we could have 19 processes that are spawned from the main process, and then we can have 20 processes running in parallel. It's still not going to be good enough because we're going to have a 1 to 2 ratio, which is still not good enough because it's going to build up a backlog of jobs. So what can we do? We can scale horizontally. So we can keep the original configuration that we had before and have 10 servers, or we can use the configuration with the better machine and have 2 servers. Now, the thing is that how can we make sure that with Workaholic or with the background job processor you're building, it actually scales horizontally? If you have multiple machines and the background job processor running on multiple machines, how do you make sure everything works? Workaholic, the thing that we did is that we use Redis. So we rely on Redis. The fact that you have Redis as an intermediary means that the applications don't need to know about the background job processor, and the background job processor doesn't need to know about the application. The only thing that it needs is the code, the source code in the application, so it can actually execute the jobs. But that's all. It's not tied to a specific application instance, and the application's instances are not tied to a specific background job instance, which means that we can have as many background job processes as we want, instances running that we want, pulling the jobs from Redis, and we can have as many application instances as we want, and queuing these jobs. And so the only thing that they need to know is that the Redis URL for the application and the Redis URL for Workaholic. Now, the other thing is that your workers should not have a state. If they have a state, this could cause problems. In Workaholic, they have a state which is just the queue name. So they can pull from the right queue from Redis. This queue is dynamically updated every second. So this is not an issue in the context of Workaholic. Okay, so it's a dense talk. So I'm gonna stop here on the recommendation of Snacks. And I'm gonna let you ask your questions if you have any. If you have any questions. Yeah.
So I'm not super familiar with the Redis queues, but like, what are the semantics around retrying, around like, you know, if one of your Workaholic threads crashes, like how do you make sure that that job gets retried or if it times out?
If Workaholic crashes?
Yeah.
Okay, that's actually an edge case we haven't covered yet, but you know, it's an open source project. So if you have an idea of how we can do it, or if you want to suggest this, open a GitHub issue or pull request, but it's not something we have covered yet. What we do is that if you interrupt it manually, we're gonna make sure they're retried. We're gonna make sure they shut down gracefully. But if the background job itself crashes, what you could do is you can not remove the job from the queue until it's actually successfully executed, for example. So that's what I think Sidekick does some of that. They have like a safe queue for their paying version. So, but it's not something we implemented yet.
Got it.
Close.
So my first question, how does this compare, or maybe I missed this, how does this compare to Rescue, which is a Ruby-based background job processor, again, or using Redis?
Yeah, so Rescue only uses processes as far as I know. So what they do is that when you want to spawn a new worker, you fork a process from the main process. So you have a child process. Here we're using concurrency and we're using threads. And we're also using the forking of processes. Now, Sidekick uses threads. So that's why it's so much faster and Rescue in certain scenario. And we're using kind of the same thing in terms of compared to Sidekick, but we're using both. We're using forking processes and also using threads. So concurrency and parallelism.
And what's the core reason for this? Is it because you're trying to...
Just for efficiency. So you can have process more jobs at once.
As opposed to, for example, spinning up like 10 more EC2 instances, or so this is about squeezing more efficiency on a single VM that's presumably running this process.
Yes.
Okay.
Yeah.
Got it. And second question, so, you know, Redis is an in-memory store, and while yes, you can serialize, as I recall, it's only going to do that for you after a certain number of operations. What happens if Redis itself dies in the middle?
Yeah, that's a great question. So Redis has, it takes database snapshots to persist to disk, which means that you could use that as a system to persist to disk in case Redis crashes. As you said, it's in memory data store. So it's configurable by the user, so they can have, like by default it's 5 minutes, I believe, but you can use a different. That's also one of the reasons why we use Redis, because it also stores.
So you could lose up to 5 minutes of jobs.
Yeah, if you use the
this
default
system.
configuration, you use up to 5, but the user itself can configure it based on their use case. If they're really like, they don't want to lose any job, they could save every, I don't know, like 500 milliseconds or even more often. Yeah. Any more questions?
Hi there. When you guys were designing this and thinking about the features, did you take any inspiration from the other enterprise message queue systems that have existed, like in the Java world, there's ActiveMQ. People in the open source world love the RabbitMQ product. Sounds like the concepts of the parallelism and the concurrency, they've existed in the past. This isn't like totally revolutionary, right?
Yeah.
This is now in the Ruby world.
Yeah,
okay.
we definitely looked at what the implementations in Ruby, take some inspiration. We didn't look at other languages. We doubled around, like we looked at Python a little bit, but really not that much. We looked mainly at Sidekick and Rescue because they're the two main ones. So yeah, there's a lot of inspiration from them, and looking at the way they solve their problems, so we can inspire ourselves from that as well. Yeah.
Merci, j'apprécie votre explication.
De rien.
Non, pas drôle.
Okay. Thank you. Okay, so this part is going to be a little shorter. So then, now, okay, we solved the problem of our scenario. So now we're efficient enough. But how do we compare to other background job processors such as Sidekick, which is a gold standard and which is known for being really efficient in the Ruby ecosystem? So what we did is that we started benchmarking against Sidekick once we felt like we were mature enough. So here we can see that we were not doing really well, right? So we were up by a factor of 2, and for the enqueuing, almost a factor of 4. So we started looking at, okay, so we're way worse on both ends, enqueuing and processing. So what could it be? It's a bottleneck that's on both ends. So we started thinking about maybe it's serialization. We're using YAML to serialize our job and deserialize our jobs. Then we looked at Sidekick. Sidekick is using JSON. So we decided to implement JSON as a serialization system. And what we discovered is that we were actually performant as like on par with Sidekick's performance if we use the same serialization. So that was a great accomplishment for us because we realized that we had a really efficient background job processor. Here we're a little more performant for processing, but Sidekick is a much more mature solution. It's not to showcase that we're better than Sidekick at all. And as I said, we're in alpha stage, so do not use this in production because it looks more efficient. Now, the other thing that we did is that we decided to use a custom algorithm. So what happens if you have multiple queues? You could optimize when you have multiple queues. And what we decided to do is that have a scenario where we have 30,000 jobs, 10,000 non-blocking, 10,000 CPU blocking, and 10,000 IO blocking jobs. We enqueue them in 3 different queues. And what we did, we benchmarked against Sidekick. We used the random polling algorithm, which gives a weight of 1 to each queue, and then it's gonna randomly poll from the different queues. It performed at 242 seconds. So we compared to our first algorithm, which was evenly balancing the workers. And what happened is that we saw we were performing much worse. So the evenly balancing workers mean we distribute the workers evenly between each queue. Now, this was not good. So we decided to implement a different algorithm that would be the ASP algorithm. It's the adaptive and successive provisioning algorithm. And what it does is that it actually distributes the workers based on the queue load. So the queue load is the number of jobs that are enqueued in a queue. And the heavier the queue, the more workers we give it. We distribute to that queue. And we performed at 327 seconds, better than evenly balancing the workers, but much worse than Sidekick. So what we did is that we decided to have a convention. We let the user flag the queues that contain the majority of IO-bound jobs. This way, what we can do is use the ASP algorithm only on these queues that are flagged as containing a majority of IO-bound jobs. As we saw earlier, having multiple threads and multiple workers for CPU-bound jobs is not useful, which means that the queues that have a majority of CPU-bound jobs, you don't need to have multiple workers on them, just one will suffice. And we realized that we performed really well, slightly better than Sidekick, which was really good for us, great victory. So now I'm gonna walk you through a bit of code that's composed the ASP algorithm. So at the start, let's say we have 25 workers. If the option for the CLI is specified, we use the ASP algorithm. So we do that by spinning up a new thread so it doesn't block the main thread. And every second, we're gonna use the ASP algorithm to redistribute the workers between the queue. Because as the time passes, the jobs are gonna be performed and the queue loads are gonna change. So what we did is that we took an example scenario. Let's say you have 4 job queues, and let's say all these queues are flagged, okay, for simplicity's sake. So at first, we're gonna assign one worker per queue. This way we ensure that each queue has one worker and it's gonna be work time. So we use 4 workers in this case out of the 25 that we have. Now then we need to calculate the average jobs count per worker. So each worker is gonna be performing a certain number of jobs. In this case, we're gonna have 52,000 jobs, around 52,000 jobs to be performed. And we have 21 workers remaining, which means that we're gonna need to perform about each worker is gonna need to perform about 2,500 workers. Now, that we have this number, we're gonna provision each queues based on that number. So what we can do is that we calculate the number of workers. So we take the first queue, for example, 50,000 jobs included in it. So it's much heavier than the other queues. So what we can do is that we calculate the number of workers based on the number that we saw earlier, here, 2,500. And so what we do is that we divide the queue load by the number, the average jobs count per worker, and we get the number of workers that we need to distribute to that queue, that we need to provision that queue with. Here we need to provision the queue with 20 workers. So we do that. We provision the queue with 20 workers. You go, nice animation. And then we provision the second queue. The second queue has 2,000 jobs and we have 1 worker remaining. So the math is easy. We provision the queue with 1 worker. So we've used all our workers, which means we don't have any workers left to distribute. And so this concludes the example of the ASP algorithm. Okay, so now the last core feature that we thought belonged in a background job processor is reporting. You want to make sure that your users are going to have a way to see different statistics about your job so they can make better decisions about their background job system. Okay, so for Workaholic, we have real-time data, as I stated at the beginning of the talk, and we have historical data. This is the web UI that we implemented. So let's start with real-time data. How did we solve the problem of having real-time data? So at first we thought, how much data should we store? So we thought we would store 1,000 seconds of data. So we would have 100 data points on the web UI, and then we would pull every 10 seconds from the front end to the back end, and it's running in a Sinatra app, by the way, the web UI, and so the web server for the web UI. And so every 10 seconds, the front end pulls the data. We store this data in Redis not to add a new dependency. And the way we do that is by using, once again, sorted set. So by using the sorted set, we can actually retrieve the jobs in an easier way because we can just use the timestamp, two timestamp, a range of timestamps, and then retrieve all the members that are between that range of timestamps. And so the way we store it is that as a score in the sorted set for each member, we store the score is when the job was completed or when the job failed in the case of a failed job. So this is what the web UI looks like. If you have the processing throughput, have the memory usage, and then you have the number of jobs that are enqueued, the total number of jobs. Now let's talk about historical statistics. So historical data is a different challenge because it's a lot more data, right? So what we wanted to do is store an aggregated number of this data, so a count of the data, a count of the completed jobs, a count of the failed jobs. So what we did is at first, we decided to use the sorted set the same way, but so we can retrieve easily, as you can see here, the Z range scope by score command that Redis provides us with is a really easy way to retrieve data. But the problem with that was that we had to actually get the score first, get the aggregated count first, then we had to remove it from Redis, and we had to increment it in our code, and then put it back. So the problem with that is that we had concurrency issues. And the thing is that we were storing 1 data point per day, which means that we had 1 timestamp per day. So we had to change the same member in the solid set multiple times. So what we decided to do is push the computation down to the Redis level. So how did we do that? The way we did that is by using a different data type that Redis provides us with, which is the hash. Because it provides a hash data type that actually has h-incobay command. This way, Redis makes sure the command is performed in an atomic way, And this way you cannot run into race conditions. So that's how we store data. Now our goal was to store 365 days of data. So what did we do? At first we computed the average size of a hash field in a hash. So it takes about 8 bytes after doing some calculations. And what we did is that we ran some estimations. Let's say we have 25 different types of jobs, 25 jobs classes in a year. And then if we have 1 data point per day, we're gonna have a total amount of space that's 71 kilobytes in Redis, that's taken in Redis. If we have 1 data point per hour, it's gonna take 1.7 megabytes. If we have 1 data point per minute, it's gonna take 100 megabytes. So the viable option we went with was 1 data point per day, because if the user wants to display 365 days of data in the web UI, we need to send a response pretty fast. And so 71 kilobytes was what we went with, and that's 1 data point per day. So that's what it looks like. You can do 7 days ago, 30 days ago, 180 days ago, 365 days ago, and you can have the total of jobs completed and job failed, or you can have a breakdown by class. Okay, now for the nice to have features. What we have for Workaholic is a CLI. So the CLI is gonna give you full functionality of Workaholic, the number of workers you wanna use, if you wanna use the ASP algorithm, if you wanna use multiple processes, the number of connections. So that's a nice to have feature. Now, the other thing is that if you're building a background job processor in Ruby, you're gonna wanna integrate with Rails. So at first, we have a default configuration, We have a default configuration, which is we spin up 25 workers. That's mainly based on Sidekicks estimations, which, it is used by real applications, which means that the author of Sidekick actually ran a lot of tests and concluded that 25 threads was actually a good number. So we just inspired ourselves from that. And then the other thing is that we have a number of Redis connections based on the number of workers, and also for the extra components we have in Workaholic that necessitates a Redis connection, and that's spin up in a thread. And we only start with one process, Workaholic. So if you want multiple processes, you need to specify it in the command line. Now, for the Rails integration part, what we do is that when you load the application, if you're loading the application in the Rails root directory, what we do is that we load Rails, and we load all the components in Rails, and we also have an active job adapter that we load at the same time. Now, the final additional feature that we have was testing. So we have a test environment. We spin up an additional Redis server on which you can run the tests, and then we flush that database before each test. Now, when we were testing with Workaholic, we had a challenge for testing, which was that the thing is that if you're executing code in threads, you have no guarantee that it's going to be synchronous, because your scheduler can just stop the thread and schedule another one, which means that what we did is that we have a custom expect method, which actually is going to test for a certain duration if the result has changed, the state has changed. If it has, then it has the test pass. If it doesn't, it just lets our spec raise its normal exception. Okay, and now for the last point, we benchmarked Workaholic using MRI against Sidekick. We're on par with Sidekick's performance, which was a great achievement for us. So here it's 10,000 jobs, 10,000 non-blocking jobs, IO blocking jobs, CPU blocking jobs. And the other thing that we did is that we checked if we were running on JRuby, and we are, and we tested that as well. And we can see that we're running on JRuby as well. So this was actually not hard. We just ran Workaholic and it worked. So yeah, that's it. If you want to have more information about Workaholic, you can go on the website. We have a long write-up that explains everything that we built, how we built it. It's workaholic.github.io. Once again, my name is Antoine Leclerc. I'm a software engineer. Here's my email address and my website. I'm looking for work, so if you're hiring or if you know anyone who's hiring, don't hesitate to contact me. And also, if you want to contribute to the project, open a GitHub issue, a pull request, or also reach out to me, to my email. And that's it. Do you have any questions? Any question? Yeah. I still have the concurrency issue example if you want to see, but. The questions? Do you want to see the example? Yes, no? Yeah? Okay. Show you. Okay. So here's a little example that shows why concurrency is so tricky and you want to have the background the jobs actually be thread safe. So here we have a payment job. There's a global variable, which you don't usually want to do, but we'll just use that as an example. So the balance is 0. And what the job does is that it stores in a local variable the current balance. Then it increments the new balance 1,000,000 times. And then it assigns that value to the global variable balance. And so what we do, we spin up 10 threads. And in each thread, we perform one job. What do you think is going to happen? Any guess? Sorry? I don't understand.
Oh, this will just be some random number.
Some random number? So what should it be?
Which should be 10 million.
10 million, right? Okay, so you're right. So it's going to be a multiple of million. So why is that? That's because we have race condition, right? We are assigning balance, and then we're just incrementing with a different local variable, and then we reassign it. So you can have a thread that has a balance at 0. Then it starts incrementing 1,000,000 times. Then it stops by the OS scheduler. Then your OS scheduler schedules another thread, and then it starts, and the balance is still 0. So it starts at 0. And then when they're done executing, they just assign whatever value they were at. So 1 million in each case, in these two cases. So that's why we end up with different results every time we run it. Now I have an even trickier one, which is the same thing, except that instead of incrementing 1,000,000 times inside of the job, we just execute the job 1,000,000 times and we increment only once inside of the job. So what do you think is going to happen in this case? Same problem?
But not a multiple million.
Well, that's weird. It's not the same problem. So actually, yeah, there could be race conditions, and that's why concurrency is so tricky. So here what happens is that the operation performed inside of the job is so small in terms of computational resources that the computer makes the operation atomic because it's so cheap. But in theory, if you have a really slow computer, you could totally raise some race conditions. So that's the example I have in terms of like concurrency issues and why it's so tricky to work with. And that's also why you want to make sure the jobs that you use and that you enqueue are thread safe. That's it.
Et voila. Voila. Okay, thank you so much for the talk. That was great. So that worked out for you, huh? Excellent. We want to spend some time to, does anyone have any, yes, I see your hand up for sure. Does anyone have any announcements right now that they would like to, if you have any opportunities, if you're looking for a job perhaps,